Hello, everyone. Today we will be discussing about impact. Now, before going into today's lecture, I would like to summarize the previous lecture, which was about impulse and momentum. So, in the previous lecture, we introduced linear momentum, which is g in this case, and which is just the multiplication of mass and velocity, and g is vector, velocity is vector, and m is scalar here. Uh, in the previous lecture, we also introduced Newton's second law in term of linear momentum. So the resultant net force is proportional to an object's rate of change in linear momentum. So we can write the Newton's second law, that summation of all the forces, which is equal to ma. And we can also write this dg by dt, so which is the rate of change of this linear momentum here. And then we introduce linear impulse momentum principle. So as you can see in this equation here, that you have g1, which is the initial linear momentum, and then you have this term here, which is what we call as impulse, and which is the integration of forces from t1 to t2. And on the right hand side you have g2, which is the final linear momentum. So to say that this equation is that initial momentum plus impulse equal the final linear momentum of the of any body here. And we can also write this equation in term of a diagram, and the diagram is called is impulse momentum diagram. So as you can see in this case, that if you have a particle with initial momentum here, and the initial momentum is in the velocity, in the direction of the velocity here. So g1 is equal to mv1, which is the initial linear momentum, and plus impulse. So the impulse is in the direction of the force here, and you will integrate this from t1 to t2. And this is a vector equation. Therefore, we have to add these two terms using the head-to-tail rule to get the final linear momentum. So if we add this vector and this vector, as you can see in this figure here, so we will get the final linear momentum, which is the vector sum of g1 and this impulse term here. Finally, in the previous lecture, we also introduced this conservation of linear momentum. So if the external forces applied to the system are zero, if there is no force applied to the body, so then this impulse will be equal to zero, and then g1 will become equal to g2. So this means that the initial linear momentum will be equal to the final linear momentum of a system, and then we will say that this is the conservation of linear momentum equation. Okay, so in today's lecture, we will mainly discuss about impact, which is the application of the momentum and impulse principle. There are two type of impacts that we will define here. One is what we call is central impact, and one is oblique impact. So we will discuss these two type of impact in detail. In addition to this, we will derive equation of motion for central impact and also for oblique impact. And we will also define another very important term here, which is what we call is the coefficient of restitution. And you will see this in a minute. Okay, so first to introduce impact. So the principle of impulse and momentum have important use in describing the behavior of colliding bodies. So the impact topic is very closely linked with the previous lecture, which is about the principles of impulse and momentum. So impact refer to the collision between two bodies and is characterized by the generation of relatively large contact forces which act over a very short interval of time. So different type of impacts we can see in these figures here. So the first figure is that there will be impact between the two balls on the pool table. Uh, in this impact, there's a butt strike on aircraft here, and the impact that you see here is the car is just collide with some with a wall here. So now it's important to realize that an impact is a very complex event involving material deformation and recovery and the generation of heat and sound. So as you can see in this figure here. And now in this particular lecture, we will not be going into that much detail. We will not be discussing how the material will behave, but we will be just discussing about just the simple type of possible impact. Uh, so as you can see that impact is can be classified in mainly two types. So one is what we call is the central impact. So if you want to represent the central impact by a diagram, so as you consider, if you have two balls here, and if these two balls are in contact with each other, so what will happen is that this is the CGs. So if you consider that this is the CG of the first ball and this is the CG of this ball number 2. So if you call this ball A and ball 2, and we will obviously represent this by just particles, and the center of gravity of the first particle is this point here. The center of gravity of this particle is this point here. So now if you join these center of gravities and you extend this, so these two particles are in contact with each other, and if you draw a line passing through the center of gravities of these two particles, so this line is what we call is the line of impact. So this is the line of impact here, and if you draw a perpendicular, and which will be just passing through the contact point, so this line is what we call is the plane of impact. Okay, now in this case, if these two particles are moving along the line of impact, so this type of collision or impact is what we call is the central impact. So if you read this statement here, so the central impact occurs when the direction of motion of the mass centers of the two colliding particle is along a line passing through the mass center of the particles. So if the direction of the velocities, so the velocity of particle A is VA here, and velocity of particle B is VB here. So if the particle A is moving in this direction and the particle B is moving in this direction, so this means that the velocity A is along the line of impact and velocity B is also along the line of impact. So then this type of impact is what we call is the center impact. And this line which you draw by joining these center of masses of the two particles is what we call is the line of impact. And then the line which is perpendicular to the line of impact is what we call is the plane of impact. And this if we call this a figure A, so this is obviously our central impact. Okay, now we have another type of impact, which is what we call is oblique impact. So now in oblique impact, when the motion of one or both of the particle make an angle with the line of impact, so the impact is said to be oblique impact. Now in the oblique impact, again, if you consider two particles, this is particle A and particle B. And again, this is the center of gravities of these two particles. So again, if you draw a line passing through the center of gravities, so this will be our line of impact. And again, the plane of impact will be perpendicular to the line of impact. Okay, now in this in the central impact, the velocities of the two particles were along the line of impact. But in case of oblique impact, the velocity of particle A can be in some angle to the line of impact, and this will be the velocity of particle A, and the angle that this will make, for example, with the line of impact, will be represented by theta here. So this means that the velocity is now not in the line of impact, and similarly the B can have a velocity which may be in this direction here, and this is angle A, and this is maybe angle B here. So this type of impact is when the velocities or at some angle to the line of impact is what we call is oblique impact. Okay, so in the previous case, in the central impact, it's relatively easy to deal with because normally in impact, you will be given the masses of these particles. You will be given the velocities VA and VB before impact, and you will be asked to calculate the velocities after impact, which will be along this line in this central impact. So it will be just two unknown. Now in this case, it's relatively complicated because in addition to the velocities, its magnitude, you also need to calculate the direction of the velocities. So in this case, you will be given the masses of the particles. You will be given the VA and VB and its directions, theta A and theta B, and you will be asked to calculate the final velocities after impact. So you will need to calculate the velocity of particle A and particle B after impact, and you will also need to calculate the magnitude and direction of the velocities. So this means that in this case, in the oblique impact, you will need to calculate four unknowns, that is the magnitude and direction of both particle A and particle B after impact. But in this case, because the particle will just move along this line, so there are just two unknown. Okay, so now we will start to derive the equation of motion for the first case, which is the central impact. So if you consider two particles, so this is particle M1 with a mass M1, and this is the second particle is with mass M2. So you are given these masses, and if we draw a line here, which is the line of impact here, so which is passing through their center of gravities, and this particle may be moving in this direction, and this particle may be moving in this direction here, and the velocity of particle 1 is v1, and the velocity of particle 2 is v2. So these are the velocities before impact. So this is the before impact situation. We have these two particles, and before impact, the particle 1 is moving with velocity v1, and particle 2 is moving with velocity v2. And now in this case, if v1 is greater than v2, so at some time these particles will collide with each other. So what will happen that okay, so as an introduction to impact, we consider the collinear motion of two sphere of masses m1 and m2. So as you can see in this figure here, traveling with velocities v1 and v2. So the velocity here is v1 and velocity here is v2. If v1 is greater than v2, so as you can see in this case here, collision occur with the contact forces directing along the line of center, and this condition is called the central impact. Uh, so as you can see here that in second case, what will happen that these two bodies will collide with each other. So again, this is particle 1 and particle 2 here. Okay, so following initial contact, a short period of increasing deformation take place until the contact area between the sphere cease to increase. So if these two bodies will impact with each other, and assume that these are elastic bodies, so the contact area between the two bodies will increase gradually until the contact area between the sphere cease to increase. So this means that at this instant of time, we will have maximum deformation. So now this is our maximum deformation. This is the maximum deformation during impact here. And at this particular time, the two particles, that is the M1 and M2, will be moving together with the same velocity, which is, you can represent this by V naught here. And now finally, then during the remainder of the contact, a period of restoration occurs, during which the contact area decreases to 0. And in the final condition, which is shown in part C of the figure, the sphere now have new velocity v1 dash and v2 dash, where v1 dash must be less than v2 dash. So what will happen that after the deformation, so after contact or impact, when the two bodies will get separated, so now, and they will recover from the contact, and again these will be moving along the line of impact. But in this case, the velocity, for example, we are representing this by this dash here, so v1 dash and v2 dash. So, and again, this is a particle with mass m1, and this is particle with mass m2. The masses before impact and after impact will remain the same. It will not change. So now in this case, as you can see that after the impact, now v2 is greater than v2 dash is greater than v1 dash. So these are the main three events that occurs during the impact. So this was before impact, v1 was greater than v2, and the bodies were moving along the line of impact. So this is our line of impact. And therefore we call this central impact here. And now the two bodies collide with each other, and then at one point we will get the maximum deformation between the two bodies, and at that maximum deformation, the two bodies will then moving with the same velocity, which is we representing this by v naught, and then it will then start recover from the impact. And then after the impact, as you can see in this figure here, that now the two bodies will get separated from each other, and particle 2 is now moving with velocity v2 dash, and particle 1 is moving now with velocity v1 dash, which is after impact. And in this specific case, v2 dash is greater than v1 dash. So these are the three main events which occurs during the impact here. Okay, so if the impact is not overly severe, and if the sphere are highly elastic, they will regain their original shape following the restoration. So as you can see in this case here, With a more severe impact and with less elastic bodies, a permanent deformation may result. For example, you can assume that when two cars collide with each other, and as you can see this F1 and F2. So F1 and F2 are the contact forces. So F1 is the force, is the contact force of particle 1 on particle 2, and similarly F2 is the contact force of particle 2 on particle 1. And these forces are equal and opposite, as you can see in this case here. Now the contact force are equal and opposite during impact, and therefore the linear momentum of the system remain unchanged. So here we can apply the law of conservation of momentum, but this law of conservation of momentum will be applicable to the whole system, which in this case consisting of two particles. You cannot apply the law of conservation of momentum to one particle, but you can apply this to the whole system here. So what here you can write that G1, which is the initial momentum of the system before impact, should be equal to the final momentum of the system, which is after impact. And we know that the momentums are vectors. So therefore, we have these arrow on the top of it. So here you can say that momentum. So this G1 is momentum. So G1 is the momentum of a system before impact, and similarly G2 is the momentum. So G2 is the momentum of a system after impact. And we know that because the forces, which is F1 and F2, are the same and opposite to each other, so these will cancel each other, and therefore we have this law of conservation of momentum here, which we can apply here. So in this case, if you see here, this is for the whole system. So G1 is the momentum of a system before impact, which is this situation here. So in this case, the momentum of particle 1 is m1 v1, and the momentum of particle 2 is m2 v2. So the m1 v1 and plus m2 v2. So this is the momentum of a system before impact, and momentum of a system after impact is m1 v1 dash, which is here after impact. So m1 is the mass of particle 1, and v1 dash is now the velocity of particle 1, and similarly mass of particle 2 is m2 and its velocity is v2 dash. So now we have this equation that we can write for this impact, which happened before the two particles. Okay, now here there is an issue here. So as you know that in case of momentum, you will be given in case of impact, you will be given the masses and initial velocities. You will be given m1 and m2, and you will be given v1 and v2, and you will be asked to calculate v1 dash and v2 dash. So this means that you need to calculate two unknowns, v1 dash and v2 dash. But in this case, we just get only one equation, which is not enough to solve to solve this system, or to calculate v1 dash and v2 dash. So definitely we need one more equation, and then we will be able to calculate v1 dash and v2 dash. Okay, so from here where we will get that equation. So that equation that we will get from this new term, which is what we call is the coefficient of restitution. So the coefficient of restitution will be used mainly to derive another equation, which we should use with the law of conservation of momentum for the whole system. to calculate the final velocities v1 dash and v2 dash. So now for a given masses, which is m1 and m2, and initial velocities v1 and v2. So the momentum equation contained two unknown, that is v1 dash and v2 dash, obviously. And clearly, we need an additional relationship to find the final velocities. So from where we will get that equation, this relationship must reflect the capacity of the contacting bodies to recover from the impact, and can be expressed by the ratio E of the magnitude of the restoration impulse to the magnitude of the deformation impulse. So this E, which is what we call is the coefficient of restitution, is simply the ratio between the restoration impulse and deformation impulse. So as before writing this equation, if we try to write or draw the diagram here. So if you consider these particles m1 and m2, and during the impact, we will have two phases. One is that the bodies will get deformed. So that is what we call is the deformation period. So in the deformation period, you will have a contact force, which is what we call is FD. So again, FD will be the same on this particle and this particle. And this particle is obviously moving with, initially it was moving with the velocity v1, and this was moving with velocity v2. And then at the maximum deformation, the velocities were same, so then it become v0. And then in the next phase, which is the restoration, so during the restoration period, now the two particles will recover from this maximum deformation. So from the impact, which is what we call is the force here will be represented by Fr here. And again, this is particle 1 and particle 2 here, and these are their masses. And after deformation, the velocity will be v1 dash, and this will be v2 dash. And these forces, which is Fd, will be the force which will start when the two bodies will just be in contact with each other, and this will increase. And then after getting to the maximum force, it will again start to decrease. So if you draw this contact force here, so if we call this F, so it will start at 0. So 0 time is then when the two bodies just get in contact with each other, and this contact force will, for example, increase, and it will go to the maximum here, and this is our time here. So it will start from 0 time, it will get to this time, which you can call is, for example, t0. And then again, when the two bodies will restore from the contact, so, and when the two bodies will be about to separate, so the contact force will become equal to 0. This is how the contact force is changing during the impact. So during the deformation period, the force is what we are represented by Fd, which is this force from 0 to t0. And then from t0 to t, which is what we will have is the restoration force here. So this force here is what we call is Fd, and this force, which is from the peak value to the 0 value, is what we call is the Fr here. And the time from 0 to t0 is the time when you get the maximum deformation. And then from t0 to t, you will get the body will recover completely from the impact. So now in this case, the E, which is the coefficient of restitution, is the way we define is the ratio E of the magnitude of the restoration impulse to the magnitude of the deformation impulse. So impulse is just the integration of force with respect to time. So the restoration impulse is from t naught to t. So if you integrate this force from t naught to t, and the force here is Fr dt, and if you divide this by uh, and then you have the time for the deformation, which is from 0 to t naught, and Fd dt. So this is what we call is the coefficient of restitution. So the coefficient of restitution is just the ratio of the restoration impulse, which is the integral of the Fr with respect to time, to the deformation impulse, which is again the integral of force with respect to time. And as you can see from this figure here, that the deformation is from 0 to t naught, and the restoration is from t naught to t. So this is our equation for the coefficient of restitution here. So this E is what we call is the coefficient of restitution. In this case, Fr and Ft represent the magnitude of contact forces during the restoration and deformation period, respectively. So as we explained in this figure here. Okay, so now we have this diagram here. So now how we will get that second equation? The way we will get that second equation is that now we will apply this E to each individual particle. So for particle 1, the definition of E together with the impulse momentum equation is given here. So this is the impulse momentum equation, which is G1 plus impulse equal to G2. And here we have the coefficient of restitution, which is the restoration impulse divided by the deformation impulse. And this is the main diagram that we draw on the previous slide. So during the deformation period, you have this Fd, which is the deformation force, and then during the restoration period, you have this diagram. So the forces between the two particles is Fr. Now, if you consider this as a whole system, then Fd and Fd and Fr on both particles are exactly the same. So this means that Fd on this particle and this particle are the same and equal and opposite. So there will be no overall external force here. So that will cancel each other. So this means that for the whole system, there will be no effect of the Fd on this equation here. But if you consider one particle only, which is we are doing here, so if you consider only one particle, then the one particle we cannot apply the law of conservation of momentum. Then we will need to consider the deformation and restoration impulse here. So if you consider particle 1 here, so for particle 1, if we use the impulse momentum equation during the deformation and restoration, so what we are doing here, that you consider the particle 1, which is of mass m1. Now before impact, the velocity of this particle was v1. Now during the maximum deformation, the velocity of this particle was v0, and after impact, the velocity of this particle was v1 dash. So now if you apply this equation, which is the impulse momentum equation to particle 1, so how we can write this equation, that we can apply this equation during the deformation period and during the restoration period. So if we apply this during the deformation period, so during the deformation period, as you can see, the initial momentum is m1 v1, so which is this g1 here, so which will be m1 v1. And then on particle 1, we have a force which is FD. So FD is acting on particle 1 here, and as you can see, the velocity is positive in this direction. So if we take this as our positive direction, so if this is our x and this is our y here, so the velocity is, we are taking this as positive here, but now the FD is in the negative direction, so this should be a negative force here. So the impulse should be with a negative sign here because it's in the negative x direction. So the impulse, we will write that from and as you can see in this force, that this FD will act on this particle from 0 to t naught. So the time here is from 0 to t naught, and then the only force that we have here is FD. So you will have FD here and dt. You will integrate this FD with respect to time, and then this should be equal to the final linear momentum, which is g2 here. And in this case, as you can see, g2 will be equal to m2. G2 in this case will be equal to m1, because this is only applicable to particle 1. So it will be m1 and v naught here. So this FD is changing the velocity of particle 1 from v1 to v naught. So therefore we can write this equation that m1 v1 minus this impulse equal to m1 v naught. Now we can simplify this equation, and we can try to get the value of this deformation impulse here. So if you try to get this value from this equation, FD dt, so this will become equal to m1 v1 minus m1 v naught. So we get this this equation from here. Okay, now in addition to this, now we can apply the same equation, impulse momentum equation, during the restoration period to the particle 1. Again, we are applying this to the particle 1. So this is, again, this was the deformation period, and now we can say we are applying this equation to the restoration period. Okay, so during the restoration period, what you have here is that before the restoration, the initial momentum was m1 v naught before the restoration, and then you have this this force which is the restoration force. So you will integrate the restoration force with respect to time, and as you can see, the restoration force is acting from t naught to t. So you will, again, this is in the negative direction, so you will say it's from t naught to t, and it is fr dt, and this will be then equal to the final momentum, which is in this case will be m1 v1 dash. So now from this equation we can also get the value of this restoration impulse here. So t naught to t fr dt, which will become equal to m1 v naught minus m1 v1 dash. So we get this these two equations here. So now for particle 1, now we have the equation of the deformation impulse, and we have the equation for the restoration impulse in terms of their masses and velocities. So now we can define E based on these equations for particle 1. So now you can say that for particle 1, you will have E. So you will just divide this equation. So m1 v naught minus m1 v1 dash, divide by this equation, which is m1 v minus m1 v naught. And because m1 is everywhere, so it will just cancel, and what you will end up is v naught minus v1 dash and divided by v1 minus v naught. We end up with this equation for particle 1. Now in this equation, as you know that in the previous case it was two equations and one equation, and we were trying to calculate the final velocities here. So here we derive another equation, but the problem here is that now v naught is also unknown, which is the velocities when the two bodies will be moving with the same velocity. We don't know v naught. We know v1 and we want to calculate v1 dash and v2 dash, but we don't know v1 v naught. So this means that in this equation we get another equation here, but in this equation, in addition to v1 and v1 dash, we also have v naught. So this means that we get two equations now, and but now we have three unknowns. So now we have two equations. So three unknown are that you need to calculate v1 dash, you need to calculate v2 dash, but in this equation now we also need to calculate v naught. So this means that this equation is not enough to solve the problem. So now what we need to do now is that we will apply the same equation, of the coefficient of restitution to the particle 2. So in case of particle 2, okay, so in case of particle 2, again you can say that the E is again equal to T naught to T and FR dt, and again 0 to T naught and FD dt. So the definition of the coefficient of restitution is the same. So it's the ratio between the restoration impulse to the deformation impulse. Now again, if we apply the same impulse and momentum equation to particle 2 here, so in this case what we will get the restoration impulse, which will be m2 v2 dash minus v naught, and for the deformation impulse it will be m2 v naught minus v2. So now from here we can calculate v2 dash minus v naught divided by v naught minus v2. So now for the particle 2, we also develop this equation here. So in this equation now again we have v2 and v2 dash v2 and v naught. So this is for particle 2, and this equation we derived previously for particle 1, and this equation is for particle 2. Now from these two equations, now what we can say that for both particles, we can combine these equations together. So if you consider the first equation, so you can write the first equation is E and v1 minus v naught. So just you will move this v1 minus v naught to this side here. It will multiply with E, and this will be equal to v naught minus v1 dash. So this for example is our equation A, and now we can similarly develop a second equation from for particle 2, so which will be E. So v naught minus v2 equal to v2 dash minus v naught. So now if you this will be our equation B. So now if you add equation A and B, so if you add these two equations, what you will end up? You will end up with this equation here, and from here then you can calculate E, which will become equal to v2 dash minus v1 dash divided by v1 minus v2. Now this is a very important equation here. for the coefficient of restitution. So the coefficient of restitution now we can write this in term of the v2 dash, v1 dash, and v1 and v2. So there is no v naught here, which is really very good, because we don't know the value of v naught. And by combining these two equations, we managed to get rid of v naught, which is what we want. So the final equation for E is now a combination of v1, v2, v2 dash, and v1 dash. So now we have two equations. One was the previous equation that we developed for the law of conservation of momentum for the whole system, and one is this equation. So now we have two equations and two unknown, which we can now solve. Okay, now this equation you may think is hard to remember, but it's very easy to remember. Now if you look at this equation here, so what it have on the is here is v2 dash minus v1 dash, so which is just the difference of the velocities after impact. So v2 dash minus v1 dash, so which you can write is the relative velocity, which you can simply say that it's a relative velocity after impact, so which is v2 dash minus v1 dash, which is just the difference of these two velocities, v2 dash minus v1 dash, so the relative velocity after impact. And this term here, v1 minus v2, is again the difference of these velocities, so which is again you can say is the relative velocity. Okay, so the E, which is the coefficient of restitution, can be represented by this this equation here now, that the relative velocity after impact divided by the relative velocity before impact. Okay, so the previous equation that we derived for the system of particle was m1 v1 plus m2 v2 equal to m1 v1 dash plus m2 v2 dash. So now we have two equations. So if you call this equation 1 and this equation 2, so now we have two equations and there are two unknowns. You will be given E, you will be given m1 and m2, and you will be given v1 and v2. Then you will be able to calculate v1 dash and v2 dash from these two equations, solving these together. So now if the two initial velocities v1 and v2 and the coefficient of restitution E are known, then we have two equations to calculate the unknown final velocities v1 dash and v2 dash here. So this is how you will solve the problem in impact using these equations here. Now let's also define this another very important topic here, that energy loss during impact. So we know that there will always be a loss in energy during impact. So impact phenomena are almost always accompanied with energy loss, which may be calculated by subtracting the kinetic energy of the system just after impact from that just before the impact. So you will calculate the kinetic energy just before impact and just after impact, and the difference will be the loss in kinetic energy here. So where this energy goes, so this energy is lost through the generation of heat during a localized inelastic deformation of the material, through the generation and dissipation of elastic stress wave within the bodies, and through the generation of sound energy. Now there are different type of impacts that you can talk about based on the E, which is the coefficient of restitution. And this was the equation of the coefficient of restitution, that E is equal to the v2 dash minus v1 dash, which is the relative velocity after impact, and v1 minus v2 is the relative velocity before impact. So based on this this equation, which is E, you can classify the impact into different form. One is the elastic impact, so that the E equal to 1. So this means that the if E is equal to 1, so this means that V1 minus V2 will be equal to V2 dash minus V1 dash. So this impact is what we call is the elastic impact. So in case of elastic impact, the relative velocity before impact and the relative velocity after impact will be exactly the same. So in this case, the capacity of two particles to recover equals their tendency to deform. And this condition is one of the elastic impact with no energy loss. So here there will be just the velocities will change, but the difference of the velocities will be again the same. And another impact is what we call is the plastic impact or inelastic impact, and in this case E will be 0. So in this case the particles cling together after collision. So what will happen that this term here on the in the nominator, which is V2 dash minus V1 dash, so this will be 0. So this means that the a relative velocity after collision will be 0 and the two particles will cling to each other. So in this case we will have the the maximum loss in energy. But in reality, these are two extreme cases, E is equal to 1 and E is equal to 0. In reality, all the impact condition lies somewhere between these two extremes. So in reality, E that you will see in most of the numerical examples will be between 0 and 1. It can be 0.2, 0.3, 0.4, 0.5, 0.6, depend on specific problem.